If someone tells you that Mars is 140 million miles away, your first reaction is usually simple. That's far. But that word doesn't even come close to describing what that distance actually means. It isn't just far. It is dangerous in ways most people never think about. And not because of science fiction or dramatic imagination, but because of raw physical reality. When you stand in front of an audience and say, "We are going to Mars," you immediately see something change in people's expressions. There's excitement, curiosity, even inspiration. It's the same kind of feeling humans have always had when facing a frontier. It's the same mindset that pushed people centuries ago to sail across oceans in fragile ships, not knowing what they would find. There is something deeply wired into human nature that turns "we might go there someday" into "we will figure it out." But physics does not respond to that mindset. Physics does not care about ambition, hope, or motivation. It has rules, and those rules do not bend for human desire. And before you even talk about rockets or technology, the real problems already begin with something simple: distance itself. Mars is not just a red dot in the sky. It is a rocky planet about half the diameter of Earth, orbiting the Sun at varying distances, depending on where both planets are in their orbits. That variation matters more than most people realize. It means the journey is never a simple straight line. It depends on timing, alignment, and orbital mechanics that already make the mission complicated before it even begins. Then there is the atmosphere. And this is where reality becomes harsh very quickly. Mars does have an atmosphere, but calling it thin is an understatement. It is roughly 1% the pressure of Earth's atmosphere at sea level. That difference is not small. It is life-changing, literally. On Earth, your body exists in perfect balance with atmospheric pressure. You never notice it because it is constant. On Mars, that balance disappears completely. Without a pressurized suit, a human would not survive even moments on the surface. This is not because of extreme heat or cold, although temperatures can drop to around negative 60 degrees Celsius. The real issue is pressure. At such low pressure, liquids behave differently. The boiling point of water drops dramatically, below human body temperature. And since your blood is mostly water, this creates a deadly situation. It is not a metaphor. It is basic thermodynamics. Your body cannot function in that environment. So even before talking about habitats, bases, or colonization, the first layer of danger is already clear. But surprisingly, this is not even the most serious problem. Because between Earth and Mars lies something even more hostile than distance or temperature: radiation. On Earth, you never think about space radiation because you are constantly protected by something invisible but extremely powerful: the planet's magnetic field. This magnetosphere is created by the movement of molten iron inside Earth's core. It acts like a shield, deflecting a large portion of high-energy particles coming from the sun and deep space. Without it, life on Earth would not exist as it does today. Mars, however, lost most of that protection. Its magnetic field is weak and fragmented, offering almost no global shielding. Its thin atmosphere also fails to block incoming radiation. That means the surface of Mars is constantly exposed to solar particles and galactic cosmic rays. In simple terms, what Earth filters out, Mars lets in. And this is where the problem becomes far more serious than most people realize. Because space radiation is not something you feel. It is silent, invisible, and continuous. It passes through materials, including the human body, and damages cells at a microscopic level. Over time, it breaks down biological systems with precision and persistence. On Earth, this is not a concern because the planet itself handles the protection. You live your entire life inside a natural shielding system that took billions of years to form without ever thinking about it for even a second. On Mars, that protection is gone. And this is only the beginning of the real list of challenges. We have not even started the journey yet, and already the environment itself is presenting problems that are not just difficult, but fundamentally dangerous for human survival. And the danger doesn't stop once you leave Earth. In fact, it intensifies the moment the spacecraft crosses out of Earth's protective magnetic field. The trip to Mars takes around 6 to 9 months, depending on orbital alignment and propulsion efficiency. During all that time, the spacecraft is not inside Earth's shield anymore. It is floating in deep space, exposed to an environment that is far more hostile than anything most people imagine. This is where space radiation becomes a constant companion. There are two main types of radiation that matter here, and both are serious in very different ways. The first comes from solar events, like solar flares and coronal mass ejections. These release streams of high-energy particles, mostly protons and electrons, that can surge through space with enormous force. The second type is even more extreme: galactic cosmic rays. These are not just particles from the sun. They are high-energy atomic nuclei accelerated by supernova explosions and other violent events in the galaxy. They travel at near light speed and carry enough energy to pass through most materials. At first glance, it might seem simple: just build a thick enough shield. But space does not allow simple solutions. Solar particles can be partially blocked with shielding, especially materials rich in hydrogen like polyethylene. Engineers can even design a small storm shelter inside the spacecraft where astronauts hide during solar events. That part is manageable. But galactic cosmic rays are a different story. When these particles hit any material, they do not simply stop. They break apart atoms and create secondary radiation. In some cases, adding more shielding can actually make the situation worse by producing additional particle cascades inside the material. This is one of the most frustrating realities of space engineering. More protection does not always mean less danger. Even advanced ideas like magnetic shielding, essentially creating an artificial magnetosphere around the spacecraft, face massive engineering limits. The power and mass required are far beyond what current systems can realistically support for a crewed mission. So the spacecraft becomes a controlled environment inside an uncontrollable one. And every day in deep space adds to a radiation dose that slowly accumulates inside the human body. But radiation is only one part of the problem. There is another invisible challenge that begins affecting the crew long before they ever see Mars: microgravity. Microgravity might sound harmless, even pleasant. Floating instead of walking, no weight pressing down on your body. In images from the International Space Station, it looks almost fun. Astronauts drifting, flipping, playing with floating water droplets. But those images hide what is happening inside the human body over time. The human body evolved under Earth's constant gravity. Every system in it depends on that force. Bones stay strong because they constantly resist weight. Muscles stay active because they are always working against gravity. Remove that force, and the body begins to change in ways that are not helpful for survival. In microgravity, bones start losing density at a rate of about 1 to 2% per month. Over a 6 to 9 month journey, this can add up to a 10 to 20% loss in bone mass. That is not a small change. It affects exactly the bones needed for standing, walking, and surviving in a gravity environment again. Muscles follow the same pattern. Without resistance, they weaken and shrink. That is why astronauts must exercise for around 2 hours every day in space, using specially designed equipment just to slow down the loss. Even then, the countermeasures are only partially effective. The cardiovascular system also adapts in ways that become a problem later. Fluids shift toward the upper body, making astronauts appear puffy in the face. The heart senses this shift and reduces its output. Over time, it becomes less efficient in handling normal gravity again. Even balance is affected. The vestibular system, which controls orientation and motion, slowly recalibrates to a weightless environment. After months in space, the brain essentially learns a different version of up and down. When astronauts finally land on Mars, their system is no longer properly tuned for gravity. And Mars does have gravity, but it is only about 1/3 of Earth's. That means astronauts arrive physically weakened and neurologically disoriented, trying to operate in an environment their bodies are not prepared for. Then comes a more serious issue that is not widely discussed. Pressure changes inside the skull. In microgravity, fluids shift upward, increasing pressure around the brain and eyes. This can deform the optic nerve and flatten the back of the eyeball, leading to vision problems that have been observed in long-duration space missions. Some of these effects may be partially reversible, some may not. And even with exercise, medicine, and future technology, the gap between partially solved and fully safe for Mars missions remains significant. But even this is not the end of the story, because beyond the physical body, there is something equally fragile being tested: the human mind. A journey to Mars is not just a physical test. It is also a psychological one, and in many ways, an even more unpredictable one. The crew spends 6 to 9 months inside a confined spacecraft, sharing a limited space with a small group of people. There is no escape, no quick return, and no real-time support from Earth once communication delays begin to stretch into minutes. At its best, this is an isolated workplace. At its worst, it becomes a pressure chamber for the human mind. The communication delay alone changes everything. Messages between Earth and Mars can take anywhere from 3 to 22 minutes one way. That means no instant answers, no live troubleshooting, and no immediate emotional support from mission control. Every problem must be solved locally, by the crew, in real time. Now imagine an emergency in that environment, a medical issue like a stroke, a mechanical failure, a fire, or a sudden cabin pressure leak. On Earth, these situations rely on rapid expert response. On the way to Mars, that external safety net simply does not exist. Everything depends on the crew's training, judgment, and composure under pressure. This is where selection becomes extremely narrow. Not everyone who is technically qualified can function psychologically in that environment. Long duration, isolation, confined space, and constant awareness of no rescue option create a very specific mental profile requirement. We have seen hints of this in analog environments on Earth: Antarctic missions, submarine crews, and long-duration space station stays all show similar patterns. Stress increases over time, interpersonal conflicts emerge, and cognitive performance can gradually degrade under prolonged isolation. Even with careful selection and training, these risks are reduced, not eliminated. One of the most important insights from research in this area is that simulations are not reality. In every simulated Mars mission on Earth, participants always know they can leave. That knowledge changes behavior, even if it is not consciously acknowledged. It provides a psychological safety net that will not exist during an actual mission. Without that safety net, the true psychological profile of deep space travel remains partly unknown, and that uncertainty is one of the most difficult challenges to solve. But beyond the body and mind, there is still something more fundamental shaping every aspect of this mission: physics itself and the limits it imposes on communication, control, and survival. At the core of the Mars problem lies something simple but unforgiving: the speed of light. Nothing with mass can travel faster than it. This is not a technological limitation. It is a fundamental property of the universe. Because of this, communication between Earth and Mars is delayed by minutes, not seconds. Depending on orbital positions, the delay can range from about 3 minutes to as much as 22 minutes one way. That means a full conversation can stretch across nearly an hour in real time. Now consider what that means in a crisis. A medical emergency, a system failure, or a life-threatening malfunction cannot wait for instructions from Earth. By the time a response arrives, the situation may have already changed completely. This forces a complete redesign of how space missions operate. Everything must be autonomous. The crew must be capable of diagnosing, deciding, and acting without external input. The International Space Station operates in a completely different regime. It is only about 400 kilometers above Earth. If something goes wrong, rescue is possible. Communication is instant. Supplies can be sent quickly. That entire operational model depends on proximity. Mars breaks that model entirely. It is not just a longer version of space travel. It is a different category of mission. The assumption that Earth can intervene is no longer valid once the spacecraft commits to deep space trajectory. This becomes even more clear when looking at closed system experiments like Biosphere 2. In the early 1990s, 8 people were sealed inside a self-contained environment designed to simulate life support systems for extended periods. The idea was to test whether a closed ecological system could sustain human life. Problems appeared quickly. Oxygen levels dropped unexpectedly. Carbon dioxide levels rose. Food production was insufficient. The crew experienced physical weakness, psychological stress, and increasing interpersonal tension. Eventually, external oxygen had to be secretly introduced to stabilize the system. The experiment did not fail completely, but it demonstrated something important. Closed life support systems are extremely fragile, even under controlled conditions on Earth with full medical access and the ability to open a door and leave. Now imagine that system in space, where no door leads outside to safety. That is the level of difficulty involved in sustaining human life for months in transit to Mars. And when the spacecraft finally arrives, the challenges do not end. They change shape, but they do not disappear. Landing on Mars is another critical phase that combines multiple unresolved engineering problems. The atmosphere is too thin to provide meaningful braking, yet still thick enough to create dangerous heat during entry. This makes descent and landing one of the most complex parts of the entire mission. But even if landing succeeds, the crew arrives in a weakened state. Months of radiation exposure, bone and muscle loss, cardiovascular changes, and neurological adaptation to microgravity all converge at once. They are now expected to function in a completely new environment with reduced physical capability. Mars itself is harsh. Temperatures can drop to extreme lows, sometimes reaching around -80 degrees Celsius, and the soil contains toxic chemicals like perchlorates. The surface is also continuously exposed to radiation that continues to accumulate in the human body over time. Then comes another constraint that most people underestimate: return windows. Because of orbital mechanics, Earth and Mars align for efficient return travel only once every approximately 2 years. If a crew misses that window, they cannot simply leave. They must wait on Mars for the next alignment. That means a mission is not measured in months alone, but potentially in years of exposure and dependence on a fragile system. None of this is to say that going to Mars is impossible or not worth pursuing. Expanding human presence beyond Earth is a powerful scientific goal. It drives innovation, knowledge, and understanding of our place in the universe. But the key issue is honesty. Many public discussions simplify these challenges into problems that sound closer to engineering hurdles than fundamental physical, biological, and environmental limits. In reality, each major category, radiation, physiology, life support, landing, and psychology, is still an active field of unresolved research. The gap between we are studying solutions and we can safely send humans is large and often underestimated. Mars is not just far away in distance. It is far away in conditions, in survival requirements, and in system complexity. The distance itself is only a number. The real danger is everything that number contains: radiation exposure, time in microgravity, communication delays, mechanical risks, and psychological strain, all stuck together in a single mission profile. And until each of those problems is addressed with full scientific and engineering rigor, not optimism, not enthusiasm, but proven reliability, we are not truly ready. Not yet. If you want more deep space science breakdowns like this, subscribe and stay tuned for the next video.